Okay, this video is from Chapter 2, Section 5, and the title is Complex Zeros and the Fundamental Theorem of Algebra. What you'll learn about, we have two major theorems that we're going to take a look at in this lesson. We're going to talk about complex conjugate zeros and factoring with real number coefficients. And why we're going to learn this, these topics provide the complete story about the zeros and factors of polynomials with real number coefficients. So here's our first major theorem, the fundamental theorem of algebra. A polynomial function of degree n has n complex zeros, both real and non-real. Some of these zeros may be repeated. So if you think about what this means for a second, we have to recall what complex numbers are. Remember, a complex number in general form is a number that can be written a plus bi, where a is what we call the real part, and bi is what we call the imaginary part. Complex numbers can take on many forms. They can be just real numbers. Okay, so if b is 0, there will be no imaginary part to the complex number. It is just strictly a real number. If a were 0, then we would have just an imaginary part, and there's where we get our strictly imaginary numbers. So all numbers that we take a look at can be broken up into two sets, either real or imaginary numbers, but all of those numbers fall under the category of a complex number. Another theorem that we have is what's called the linear factorization theorem. If f of x is a polynomial function of degree n greater than 0, then f of x has precisely n linear factors, and f of x equals a times the quantity x minus z sub 1 times the quantity x minus z sub 2, and so on until we get to the final factor x minus z sub n. And the z sub 1, z sub 2, and z sub n are all complex numbers. A is the leading coefficient, and like I said, the z's are the complex zeros. The z sub I are not necessarily distinct numbers. Some may be repeated. When you see this z sub I and you see an I subscript, I represents the index. So we have a listing of factors in general, complex zeros, and we categorize them, we index them, and that's what this z sub I represents. So here's some connections that we need to make. The following statements about a polynomial function f are equivalent if f is a complex number. Number 1, x equals k is a solution or root of the equation f of x equals 0. Number 2, k is a 0 of the function f. And number 3, x minus k is a factor of f of x. Here's an example. Write the polynomial function in standard form. Identify the zeros of the function and the x-intercepts of its graph. So standard form, if you recall, standard form is a function where we have f of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1, and so on until we get down to a sub 0. So we want to basically do what's called expand this out or multiply this out. When we do this multiplication, we wind up with a function of x squared plus 9. Has two zeros, 3i and negative 3i. But because the zeros are not real, the graph of f has no x-intercepts. Remember, x-intercepts of a function tell us the real zeros of the function. So just because a function doesn't have x-intercepts doesn't mean it doesn't have any zeros. It just means that the zeros are not real. We see those two numbers, 3i and negative 3i, those two numbers are strictly imaginary numbers. They have no real component to them. So here's something dealing with complex conjugate zeros. Suppose that f of x is a polynomial function with real coefficients. If a and b are real numbers with b not equal to 0, and a plus bi is a 0 of f of x, then its complex conjugate a minus bi is also a 0 of f of x. So an application of that, we want to be able to write a polynomial function of minimum degree in standard form with real coefficients whose zeros include negative 3, 3 minus I, and 2 plus 5i. And if we apply what we just looked at, Negative 3 is a real number So we know that one of our zeros is negative 3. 3 minus I is an imaginary number, so we know that we also have 3 plus I as a 0. 2 plus 5I is a 0, but the zeros occur in conjugate pairs, and here's the conjugate pair for 2 plus 5I. We have 2 minus 5I. So in this case, we're going to have 5 zeros. So because the coefficients are real, and 3 minus I is a 0, 3 plus I must also be a 0. Therefore, here are the two factors that come from those. Similarly, 2 plus 5I must be a 0 since 2 minus 5I is a 0. So here are the two factors that we get from those zeros. And because negative 3 is a real 0, x plus 3 must be a factor as well. So now we're asked to put this in standard form. So we know all the factors. Now the task becomes multiplying all those factors together to get a polynomial that's in standard form. And as you can see here, this is a lot of work. Here is our f of x written in factored form. Here we have 1 factor, 2 factors, 3 factors, 4 factors, 5 factors. Now all of this work here, the x plus 3 factor, we're not going to do anything with it at first. All of this work here, between here and here, is multiplying these two zeros that come from complex conjugates. So all of this work here, 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 and here gives us this factor here. And here we have these two complex conjugate factors. Multiplying them all together gives us this factor here. So after we multiply our complex parts together, we have 1 linear factor and 2 quadratic factors. And then from there we have to use the distributive property and multiply those all out. Finally, we have an end result of x to the 5th minus 7x to the 4th plus 33x cubed minus 25x squared minus 352x plus 870. So that's some tedious work, but it's nothing more than the distributive property and remembering how to multiply and deal with complex numbers or imaginary numbers. Every polynomial function with real coefficients can be written as a product of linear factors and irreducible quadratic factors, each with real coefficients. And if I back up for a second, we see an example of that if we work in reverse. If we started off with this as our original function, we could work our way back to this step here with some factoring, some synthetic division, our rational zeros theorem. We could work our way back to this line here, which shows the product of a linear factor and 2 irreducible quadratic factors. So that's basically what this blue box says. So here's another example of that. Write f as a product of linear and irreducible quadratic factors, each with real coefficients. So go ahead and pause the video now and try this. And when you're ready, play the video and we'll take a look at the solution. So the rational zeros theorem provides the candidates for the rational zeros of f. We could list those out. The graph of f, if we look at that on our calculator, suggests which candidates to try first. Using synthetic division, find that x equals negative 1/3 is a 0. So again, using our rational zero theorem and our graphing calculator to take a look at the picture of the graph, we can determine that x equals negative 1/3 is in fact a 0. That gets us started in the process of breaking this polynomial down to a product of linear factors and irreducible quadratic factors. So our first factor, right here, x plus 1/3, that comes from the 0, negative 1/3. After we do the synthetic division process, we are left with 3x to the 4th minus 24x squared minus 27. But if we factor out a greatest common factor of 3, we make this quartic that's in here a little bit easier to work with, a little bit easier to factor. Anytime you can factor out a greatest common factor of what you're working with, please do it. So we'll put that 3 out here in the front. Then take x to the 4th minus 8x squared minus 9 and factor that into a product of 2 quadratics, one of which we can factor further. X squared minus 9 can factor into these two linear factors. X squared plus 1 does not factor. So our final result is the constant 3, are 3 linear factors and 1 irreducible quadratic factor. So some review problems for you here. These problems cover the lesson. Pause the video now, try these in your notes. When you're ready, play the video, you can see the solutions. Hopefully you get these right. If you don't, maybe by checking the answers you can see what you did wrong. If you have any questions about these problems or anything in the video, please be prepared to ask about those in class.